Okay. We're going from a lot of theoretical stuff to much more applied physiology at this point. And we're going to be talking about processes that involve endocrinology, not a little less on the basics of endocrinology. So you're putting in place the material you've learned so far. You have learned it so far, right? Okay. The material you've learned so far and putting it into context of various systems. I'm trained in reproductive endocrinology, so I'm going to start in the reproductive tract. And I'm going to start with the simpler sex, males. Okay? You've heard that before. It's true. And so this is the kind of the outline. We're a little bit on adult anatomy. I'm going to skip over embryogenesis and sex determination, hormonal controls, and puberty to get down to testicular anatomy, meiosis, and spermatogenesis, because that's germ cell production. And we'll come back to the developmental stuff later. This is something you probably would have seen in high school sex ed class or something like that. And it's just a refresher. If you've had physiology or anatomy and physiology, you have seen this before. Okay. This is an adult human with the testis located in the scrotum, which extends down from the base of the body cavity. It's outside the body cavity. This is not true in all mammalian species. There are many mammalian species where the testis resides in the abdomen, but it is true for primates. The testes are covered with a tunica albuginea, a tough fibrous coat. They are well vascularized, and the vascularity, along with nerve fibers, come down along with the vas deferens through this hole, essentially in the abdominal wall, into the testicular area. They follow. There's a fat pad that sits over this area, but there's lots of vascularity. Nerve cells come down through that. This structure is the epididymis. A lot of physiological development occurs in the epididymis. So the structural changes that make mature sperm largely occur in the testis. Physiologically, there's lots of change that occurs here, and subsequently sperm are delivered through the vas deferens and down then through the common urethral opening that runs through the prostate first and then through the penis. There are accessory glands here, the seminal vesicle, the bulbourethral gland. These are adding components that are supportive of sperm function to semen before it's ejaculated or before it leaves the male reproductive tract. There is the ampulla is where sperm tend to be stored prior to ejaculation in mammals. The prostate is another contributor to seminal fluid. And this is the structure, since it grows around the common urethra and the ducts, if this gland overgrows or becomes fibrous, it's going to cause problems not only with sexual function, but with elimination of urine. Okay, so the structure of the penis shown here. There is a retractile covering called the prepuce, which is removed if the male was circumcised. This tissue here in a non-circumcised male is covered with mucus. It tends to be like the interior of your mouth, for instance. So it's an epithelium. If the prepuce is removed in a circumcision, it becomes much more like surface epithelium. It's tougher. One of the interesting findings in the work on AIDS was that one of the best ways to prevent transmission of AIDS is circumcision, because it makes this area less penetrable by the virus. Okay. This tissue, here we go, the spongiosum is well vascularized, and that is what becomes erect during sexual activity. And it's largely because the outflow, the venous outflow, is blocked. Not so much the arterial inflow, but the venous outflow is what's being controlled. The other structure here, the corpus cavernosa, this is also capable of erectile function in terms of being engorged with blood. In a lot of species, many of the larger animals, there are also ligaments or bones that exist in this structure. So it makes it even more stiff. So particularly in animals like horses and cattle, you're going to see not only the soft tissues, but a bony tissue that actually is part of the structure of the penis. Okay, so I think that about does it on general anatomy for the male. Skip over that. We'll see this later. You've seen this before.
So many times.
Okay. All right. Testicular anatomy. Okay. This one I think I've gone over partially before. This is just a dissected testis and showing you the epididymis surrounding it and a bit of that fat pad and the vas deferens extending up toward the abdomen. The testis itself is organized in this manner. The tubules extend from what's called the reedy testis, or the area of collection of the tubules, into kind of lobes of testicular tissue. In between the seminiferous tubules, you'll find the Leydig cells. The Leydig cells are the ones that respond to LH to make testosterone. Sertoli cells and the germ cell, various germ cell stages are the ones that occupy the space inside the seminiferous tubules. Once the sperm, the structurally matured sperm is into the reedy testis, it will enter this epididymal tail. Notice how convoluted this is. Very well vascularized. It's in this area where sperm, so-called mature sperm, are coated with proteins from the male reproductive tract. It tends to slow them down, make them less motile, and they are, and at this time, they are undergoing metabolism, which is supported not so much by glucose, but by fructose. And it's very dependent on the presence of potassium. So there's a sodium-potassium shift in the medium. And they also will utilize some rather other strange molecules for their metabolic support. So wonderful things that are polyamines, things like putrescine, cadaverine. Okay. are going to be found there. All right. So structural maturation occurring here. Physiological maturation largely occurs here. Final maturation of sperm does not take place in the male. It actually takes place in the female reproductive tract. This is a cross-section of those seminiferous tubules, and the one thing you'll see is that there are different stages of germ cell development that seem to be represented in each of these cross-sections. And we'll go through that in a minute. What you will notice is near the outside rim of these seminiferous tubules, there are dark stained cells. And those are the germinal stem cells. Those are the good, come on. Those are the male germ cells, spermatogonia. The various early stages of the spermatogonia. Now, spermatogonia multiply mitotically and meiotically. So if they commit to meiosis, they will ultimately become sperm. But until that time, they continue to mitose. So adults, after the time of puberty, will have testes that include dividing male germ stem cells, whereas in the female, you won't see that. These are other pictures. Here's a more enlarged picture of what I just showed you. This is a scanning electron micrograph showing you matured sperm tails extending into the lumen of the seminiferous tubules. Down here at the baseline are spermatogonia. And there are various stages of sperm cell development that are scattered up toward the lumen and are actually embedded or surrounded by Sertoli cell cytoplasm. So if you took this picture and blew it up and drew a picture of it, you'd see something like this. Now there are some cells, myoid cells that occupy space around the basal lamina to help form this wall around the seminiferous tubules. So blood vessels are exterior to these seminiferous tubules. There's no blood in here. Okay. The Sertoli cells are these huge tree-like structures that actually have cytoplasm extending down to the basement membrane and all the way up to the lumen. And these various stages of germ cell growth, development, are scattered in that cytoplasm. So spermatogonia are the ones nearest the basal lamina. As you get further up, you're going to see later stages in meiosis. So here's a spermatogonia that probably is reproducing mitotically. This one is probably, so this might be a type A spermatogonia. Here might be a type 2, which is committed to meiosis. Once it's committed to meiosis, it will continue and it'll form spermatocytes, which are later stages. And ultimately, you get to spermatids. And finally, matured spermatogonia. Notice there's still a little cytoplasm on some of these earlier stages of spermatogonia. And finally, you get the mature sperm cell where there's very little cytoplasm. And essentially, it's essentially a tail on the nucleus. Okay. We've gone through this slide before. This is what I wanted to get to. This is data on what sperm production looks like, particularly it was taken based particularly on rodent data, but it's since been proven to hold for virtually all mammals. So the way this is arranged is you've got the basal compartment right near the basement membrane of the seminiferous tubules. And up here is the lumen for the seminiferous tubule. And this is time in days in moving from this earliest stage that's been identified as M, and all the way out here to 60 days when you've finally got mature sperm showing up. Notice the time frame. It's not hours. It's many days, multiple weeks. In rodents, this is about 10 weeks. In humans and primates, it's about 7 weeks. So it's over a month to go from this earliest stage to the latest stage. Now, the way this is organized, here you're showing mitotically active spermatogonia, A1s and A2s and A3s, A4s, and then you get to B-type spermatogonia, which are the ones that have for some reason have made a decision that they're undergoing meiotic division rather than mitotic division. And they will get into the preleptotene, leptotene, zygotene, pachytene, and diplotene stages of meiosis 1. So here's meiosis 1. And once you've gotten to this stage, you're in all of these stages, you're seeing primarily, well, spermatocytes initially, and after the division of the cells, you're seeing spermatids. Spermatids, as you go into meiosis 2, and finally forming spermatozoa near the end of meiosis 2. This final maturation process where the cytoplasm is lost from the tail and the head is called spermiogenesis. Okay. The whole process is called spermatogenesis. So they're two different words.
And what's the difference between the two?
That's what I'm writing on the board.
Right.
So you're going spermatogonia, spermatocytes, spermatids, spermatozoa. And it takes weeks to go over that process, regardless of species. Okay. The end product, this is a sperm on which the outer membrane has been removed. So the only thing missing here is the outer membrane of the sperm. What you see is a nucleus that's surrounded by a specialized microsome. It's called an acrosome. That acrosome has embedded within it, particularly in the inner wall, it has proteolytic enzymes, or proteolytic enzyme precursors, that are going to play a key role in this sperm penetrating the membrane surrounding an egg, the mucus and the membrane surrounding the egg, to allow fertilization to occur. So the nucleus, the DNA is essentially quiescent. You've switched from normal chromosomal formation where you've got chromatin surrounding the DNA to something called protamine surrounding the DNA. So it allows it to pack more tightly. So tightly packed DNA. Near the boundary of this, tail, pardon me, this boundary of the acrosome, still on the head of the sperm, is an area where receptors for egg surface actually occur. So egg-sperm binding is mediated by proteins that are in this area. There is something called a connecting piece, which is a modification of the sperm tail, and surrounding much of the modified cilium, that's the flagellum of the sperm, is a whole bunch of mitochondria. And these are the mitochondria that use fructose and polyamines and are so dependent on potassium for producing ATP. So this is the engine of the sperm. And there's the rest of the tail. The tail is made up of microtubules arranged in the typical way that flagella and cilia are. So spermatozoa reach their final shape in the testis, but they gain functional maturity passing through the epididymis and the female reproductive tract. And they don't act, full activation occurs in the vagina and cervix, and final fertilization capacities only occurring in proximity to the egg. Okay. And this thing called the acrosome reaction is the actual shedding of the outer surface of the sperm head and the outer membrane covering of this acrosome. So you essentially are looking at this when the sperm is ready to interact with the egg. Capacitation involves the stripping away of those proteins that were deposited on the sperm while it was passing through the epididymis and the male tract. And capacitation is accomplished by acidification of the medium, which is something that normally occurs when semen, which tends to be alkaline, is deposited in the female reproductive tract, which tends to be slightly acidic. Okay, I'm going to skip over that and just show you a little bit about sperm-egg fusion. This is what would happen in the sperm when the sperm has undergone removal of this acrosomal cap and the exposure of the proteolytic enzymes that have allowed it to penetrate through the mucus that's around the egg at the time of fertilization, and through this outer protein, glycoprotein coat called the zona pellucida. So those enzymes are crucial to allowing sperm penetration into this, what's called the perivitelline space, and allows these recognition sites to bind to receptor sites on the surface of the egg. Once that happens, it actually triggers a calcium flux, calcium spike in the cytoplasm of the egg, fusion of this membrane and engulfing of the sperm, and then ultimately you're going to get decondensation of the sperm head with swapping of the protamines that are there for the chromatin that normally packs DNA. But that's all occurring in the female germ cell, the egg, just after the time of fertilization. Okay. We talked about male contraception at some length earlier when we were talking about steroidogenesis and the control of testosterone production in the Leydig cells in the testis. You're probably all familiar with barrier methods. You simply preventing sperm from going from the male to the female. Vasectomy, you cut the vas deferens, and although that's a surgical procedure that may be reversed, it takes a good surgeon to do that, and the dollars to support him. In addition, one other thing that comes about with vasectomy, you may not have noticed that the passage of the sperm from the seminiferous tubules out through the male urethra, those sperm never come in contact with any vascular elements. The space they pass through is avascular, which means it's an immune privileged area. If you cut the vas deferens, or you crush the testis, or damage the testis, you no longer have an immune privileged site. What could happen under those circumstances?
Autoimmune reaction.
You can get an autoimmune reaction to what?
Sperm cells.
Your own sperm cells, okay, or to other proteins in the male reproductive tract.
Immune privilege.
Immune privilege, there's no vascular space, so there are no immune cells in that space that could potentially, so they have not learned that sperm and the proteins that are associated with sperm are self, okay? So if you violate that space and allow immune cells in, they can respond, but now it's non-self. Okay. So yeah, you can get an autoimmune response. You can get an inflammation of the vas. You can get an inflammation of the testes. And depending how violent those immune reactions are, they can go all the way to destroying testicular function. Hormones, we talked about peripheral androgens with or without the use of antagonists or agonists. Let me explain this. Antagonists to LHRH. One way to turn down LH production is to give an antagonist, but it turns out if you give enough LHRH or agonists of LHRH, things that work like LHRH, you get the gonadotropes to downregulate LHRH receptors and to become insensitive to this hormone. So you can drive this down by either giving something that blocks that action, or you give something that acts like it, but you give a lot of it. The other things, there are other ways that people are trying to block sperm production specifically, and you can think of ways to try and interfere with FSH action or use of inhibins. The big problem is that in primates, including humans, adult males aren't very sensitive to FSH action, much less so than they are in the early pubertal period when spermatogenesis is just getting started. Skip over those. And where are we? Yeah, okay. So, that's spermatogenesis in males. And a bit on male reproductive function. So what we need to do now is look at the female counterpart and look at gametogenesis in females. And I'll start with the same beginning here. Slideshow. Next slide. Pretty much the same kind of a scheme. So again, a picture you've probably seen some variant of in high school sex ed. This is a sagittal section, of course, through a female. And you're looking at, here's the backbone, here's the rectum, the lower part of the large intestine. And then forward from that, you're going to see the urinary bladder. There's the pelvic bone, the symphysis. The pelvic girdle would extend all the way around this area. So pelvic bones would be up here and extending down here. The female reproductive structures are kind of tucked in between, where you've got the vagina, the cervix, which is near the opening of the uterus, and then you've got this fist-shaped organ that has a single compartment in primates, but takes a lot of different shapes in other mammals, usually two-horned. So there's mainly the body of the uterus, which is the corpus, is largely smooth muscle. And that smooth muscle is what's going to respond under the influence of estrogen to oxytocin. So oxytocin will act on that smooth muscle and cause it to contract, particularly late in pregnancy, but once you have estrogen on board, it will contract at other times as well. The lining of this structure is an epithelial lining, and it's called the endometrium. The endometrium is the tissue that proliferates during every monthly cycle or every ovarian cycle, and that is sloughed at the end of that cycle. We'll get to a picture of what that looks like as well. The occurrence of menstruation, bleeding at the end of a menstrual cycle, or at the beginning actually, let me talk about it as the end. The bleeding that occurs at the end of that